Welcome to my channel, where I talk about my science job hunt, deliver presentations, and improve on my communication skills. I'm Paul Yeatman, a microbiologist of 15 years experience, seeking a return to the lab. I can be found on LinkedIn and Twitter, and also my microbiology blog. Today I will talk about quality assurance principles and troubleshooting. Hello, and welcome to Quality Assurance, how to apply scientific principles to troubleshooting. This is a presentation I developed about 2 years ago and presented internally at my work, which is primarily a troubleshooting position. The good thing about that is I get to use my critical thinking and quality assurance skills in what's a limited capacity because it's a customer service tech support role, but it keeps me busy, and that's the main thing. So, on to this. So, I've been working in customer support for about 6 years. I began supporting home software before moving to enterprise support. The home software got offshored. Luckily, we kept the enterprise position in Melbourne, so that's all great. Previously, I was a microbiologist in the pharmaceutical industry, and due to the nature of that work, it required adherence to strict rules and procedures. A large part of that involved quality assurance, which is pretty much preventing issues before they happen, scientific method, and critical thinking. These principles have been useful outside of the scientific arena in my non-work life. For example, I've become a successful cyclist through planning, and such skills are also invaluable when providing technical support in my role as a technical support engineer. So, what is in this presentation for you? The aim is to give you an understanding of and the ability to apply scientific methods to day-to-day troubleshooting problems, which will hopefully enable you to achieve your goals. Also, an ability to determine if what someone tells you or what you read has any basis in reality. So a general understanding of scientific method can make you a better problem solver. And in the current climate of fake news, or what people like to call fake news when they don't believe it, and also conspiracy theories, rather than believe what you read or what others say, being skeptical and being able to decide what is real or correct is an important and handy skill. Often the reason why you cannot do something is that you never put in the effort. A study or two suggests that you need at least 10,000 hours of practice to become an expert. That has since been debunked, but that's a good starting point. So if you can't cook, follow a recipe and cook often. Not any good at math? Well, practice. Can't play an instrument? Practice, and then practice some more. Basically, following a set method is the opposite of winging it. Some people are good at ad-libbing, though that does not lead to consistency, which is what we are discussing today. So when you do use a methodical approach, that ensures you actually know what the problem is, you test all the variables, and you record what you did and what the results are. And that can be helpful because it lets you understand what went wrong, so you don't make the same mistakes again. It improves the process, so ideally the result you get is more consistent, which is very important in, say, manufacturing of a product, be it drugs or a widget. It improves the process so future results are better or also reach quicker, and doing things faster in work means saving time and also money. And when you document a process, it means it can be shared with others or potentially sold to others, which improves consistency, potentially not just at your site, but globally. In order to discuss this subject, some definitions need to be defined. So I will talk about what is quality assurance, what science is, what scientific principles are, troubleshooting, and critical thinking. Put all of these together, give them a shake, and what you have is a great package for finding solutions to problems and for improving processes. So firstly, what is quality assurance? Well, that's the maintenance of a desired level of quality in a service or product by means of attention to every stage of process, delivery or production. So you may have heard of quality control. Quality assurance is similar. QC is reactive while QA is proactive. I'm a big fan of QA as I'd rather not deal with preventable issues. What sort of products would you like to be of consistent quality? Food, clothes, drugs, a car mechanic, a call centre operator? I'm sure you'd like quality products and rather not be the one to discover your food was tainted or your new TV was short-circuiting. With good quality assurance, your food and TV would be suitable for use / fit for purpose. Wikipedia defines science as a systematic enterprise that builds and organises knowledge in the form of testable explanations and predictions about the universe. Much of modern life arises from a history of scientific endeavour. Without science, we might still be trying to develop planes with flappy wings. So here we've got one of the first sort of concepts of planes, which moved into, say, biplanes driven by propellers, and due to the advance of science, we wound up with things like jets. All through trial and error. So next up, what are scientific principles? Scientific principles utilise science in order to test hypotheses and assumes verified theories remain valid. In science, an hypothesis is something that is unknown and untested, and a theory is something that is proven. So if anyone ever says it's only a theory, well, that means it's fact. There are 4 steps to scientific principles. You need to observe the phenomena, you need to develop a hypothesis, you need to test through experimentation, and in the end, develop a conclusion. And if the hypothesis is proven, then that's when it's a theory. As this presentation continues, you might feel it's a bit repetitive. The 4 steps above are mentioned repeatedly. This demonstrates how a consistent, reproducible process can be used to get to the bottom of a problem in order to find a solution. If a hypothesis cannot be falsified, it might be valid. However, the inability to prove something is on the same level as the inability to test, and thus an unfalsifiable hypothesis is also invalid. When developing a hypothesis, Occam's razor states that the simplest solution is probably the correct one. So the most likely hypothesis you need to test is the one you test first. According to Wikipedia, a scientific theory is a well-substantiated explanation of some aspect of the natural world based on a body of facts that have been repeatedly confirmed through observation and experiment. Such fact-supported theories are not guesses, but reliable accounts of the real world. So more about scientific principles. In science, a single variable is tested to determine if this influences what is observed. So there's not much point doing an experiment where there's 20 variables and you test all 20 variables at once, because you won't know what variable altered the result of the experiment, assuming there was a different result. So you've got to test variables each time, so then you know what the root cause of a problem was or what the actual variable does. You also use controls. These are known as variables that produce known behaviour. Conclusions must be based on records of observations. Here data is king. More data leads to more informed conclusions. You can't state that, hey, when we tested sticking a nail in water produces rust. You can't conclude that water rusts. You need to determine what causes the rust, as an example. Gathering data and building upon what is known can lead to more knowledge or improved processes in the future. Next, we will talk about troubleshooting. So, 4 steps to troubleshooting, very similar to scientific processes. So, observation, development of a hypothesis, testing via experimentation, and developing a conclusion supported by the data with scientific principles. For troubleshooting, you'll see I've got 5 listed here. You need to define the problem, similar to observation, determine what the cause might be, as in develop a hypothesis, test various solutions to the problem, so that's your experimentation, determine what the cause of the problem was, which comes into the conclusion stage, and most importantly for troubleshooting, is implementing corrective and preventative action so the problem is unlikely to happen again. So you don't want to keep making a product where, for example, you get, say, glass chips in a shell glass vial, or a clear solution continually comes out brown. You would determine why these things happen and implement the appropriate action to prevent them from happening again. Because otherwise, in manufacturing, that would be, say, an adulterated product which can't be sold, and if you did sell it, then an auditor would come along and give you a big red cross and potentially stop you from selling, which is bad because that costs money and you waste time trying to figure out what the problem is over and over again. So get a problem, determine why it's caused, fix it. Shouldn't happen again. 1 to 4 is what I do every day as a tech support engineer. I also like to include number 5 where possible, because that means that people don't have to keep calling up about the same problem. Which is good for the customer, good for you, good for everybody. What is critical thinking? Well, that's the objective analysis and evaluation of an issue in order to form a judgment. It goes hand in hand with problem solving. An issue needs to be evaluated in order to determine how best to solve it. With the proliferation of fake news, pseudoscience, or what I like to call sham science or bullshit, conspiracy theories, the ability for anyone to publish anything online, critical thinking and being skeptical is vitally important. It allows you to determine what is fact and what is fiction. A whole lecture could be devoted to this subject. Carl Sagan wrote a good book on the topic called The Demon-Haunted World. I recommend you pick up a copy. You shouldn't really believe anything anyone tells you unless you have been shown that such statements are true. So don't take what I'm telling you on face value, go out and do your own research. If an expert says it, there is a good chance that the information is correct. Keep in mind that even experts get things wrong. You also need to determine if the expert is an expert. Quite often, if you're experienced in the subject, you tend to be an expert. But you still need to determine if what the person is saying actually has truth. A primary and secondary school education is sufficient to give you a good handle on the overall quality of what people say. A baloney detection kit, as discussed by Carl Sagan's book, gives you great tools for seeking the truth and sorting the fact from fiction. I will discuss all this later. Carl Sagan was a widely respected physicist and science communicator, so therefore an expert in his field. What are examples of troubleshooting? Okay, for this talk, I will talk about 4 things. How to troubleshoot a light not turning on, determining whether the earth is flat or not. I'm bad at climbing hills, or at least I like to say I am, so how have I addressed that? Through using scientific principles. And a computer software installation fails. How would you use troubleshooting to solve that? In a nutshell, these examples demonstrate how QA techniques can be used to fix problems at work and home, how you could improve your supporting performance, and how you can decide if fake news is indeed fake. So, on to our first example, which is a light doesn't turn on. So you notice we've included the 4 main steps. So, observing the phenomenon, developing a hypothesis, testing through experimentation, and developing a conclusion. So we have to observe the phenomenon first. So what are the observations we have? We flick the switch, there's no light. The light worked yesterday. Flicking the switch on and off, still doesn't give us a light. I look for the globe in the socket, it's there. Lights on in the rest of the house? Yes, they are. I open up the fridge, the light's on in there. The power meter's spinning around, indicating that the house is using power. No fuses in the fuse box are blown, and other lights turn on when their switches are flicked. So, first bit's the problem. Number 2 is observation. Number 3 is testing, and then all the rest of the steps are observation. And after doing our observations, then we can develop causes which we can then test. Development of the hypothesis. Here I've listed the likely causes as blown globe, loose connection of the light socket, a loose connection at the light switch, maybe a mouse has eaten through the cable. And also, well, the light's not working. Let's just say aliens have replaced a globe with a fake globe. Because why not? Ideally, what you do here is test the most likely hypothesis first before trying another solution. That's based on Occam's razor, which I previously mentioned, and that states that the simplest explanation is most likely the right one. So the simplest explanation is that the globe is blown. It's really, really unlikely that aliens decided to come along and replace the globe with a fake globe. It's probably within the realms of possibility if you consider the multiverse, but pretty far-fetched. So I would say here that hypothesis 4 and 5 are invalid and not worth our time trying to examine. So let's go through our testing. What I want to do is test for the blown globe first. So I look at the globe for burnout. Is it burnt out? Yes, okay. I replace the globe and I can test the switch. What would I do if there was a loose connection to the light socket? So I've looked at the globe and say it hasn't burnt out. I could wiggle the globe when the switch is in an on position. I could remove and reseat the globe and I could test the switch. What if there was a loose connection at the light switch? I could pull apart the light switch and see if there's anything loose. Probably not the wisest thing to do if I wasn't certified as an electrician or conceivably didn't know anything about electrons and electricity. If I was to do that myself, which I don't recommend, I'd switch the power off at the main switch first. What about if a mouse is eaten through the cable? Well, that could have happened anywhere along the cord path. It's tricky and it couldn't be tested unless I pulled the wall apart. Not something I can test. What about aliens replacing the globe? Well, it's not falsifiable in principle, but as I said in the last slide, really, really far-fetched. So, after all our testing, we need to develop a conclusion. In this example, the globe had blown. So the conclusion was, or is, the light did not turn on as the globe had blown. The solution to the problem is therefore obvious. Replace the globe. In practice, you'd probably just replace the globe without any testing. I've used this example to allow you to get the general idea of how quality assurance following a defined process is useful in troubleshooting. These steps would allow you to create a troubleshooting guide for any problem you want to solve. So that's any problem at home if you really want to document how to solve stuff, or problems at work, say, I don't know, contamination always in the one spot during a batch or something like that. You could investigate what's going on, document your troubleshooting process if you needed to develop a troubleshooting process overall, and you could then document that, hey, this is our troubleshooting process for all issues that arise. And because you've actually documented your steps to solve the problem, say if that was production or manufacturing, you document that to show that, hey, you had a problem, you investigated, you solved it, and ultimately you introduced corrective and preventative action which stopped that problem from happening again, which is something that auditors like you to do and would really love you to do. One of the biggest audit observations tends to be correct process not followed or correct process not documented. So if you document your processes and follow them, that's one of the biggest ways to reduce audit citations. With this problem of a light does not turn on, how did critical thinking help? Well, by observing the problem, we can save time by not testing invalid hypotheses, e.g. no blown fuses means we don't need to replace the fuses. By testing the simplest hypothesis first, we may have seen the filament in the globe was broken, which indicates the globe had blown. Quickest amount of time to do your testing. Look at the globe, it's blown, okay, that's done. Now we just replace it. If the blown globe was replaced and the light still remained off, what we could do would be to test the remaining hypothesis as perhaps the light socket was loose too. Sometimes you'll find that the cause of a problem is not limited to a single reason. Here I would like to add that by observing the problem, we do not waste time testing complex hypotheses or even developing them. By observing the globe had blown, we would save a lot of time investigating the issue. We do not specifically look for a blown globe. By documenting the process, we know this so there's an opportunity to improve on the process. I could have come up with another hypothesis, much the same as the alien one. The light globe gnomes have replaced the globe with a dud while they improve on the original design and then install one without our knowledge. Crazy hypothesis, not worth our time investigating it. My next example is one relating to fake news or just flat out nut jobs. You could read in the news that the Earth is flat. Well, could that be true? So what we got here is the round Earth and a flat Earth based on one leading hypothesis where there's this big ass turtle and there's a whole bunch of elephants, normally 4 sitting on top, and on top of the elephants there's a flat expansive land, so presumably you need 4 elephants so the land doesn't tilt on the back of the elephant. And somehow water just rolls off the edge of the world and is continually replaced and blah-de-blah-de-blah. So, how would we actually test these two hypotheses that the Earth is round versus the Earth is flat? Well, there are 4 steps again. Observe the phenomenon. Develop a hypothesis. Conduct testing through experimentation based on the hypothesis. And based on the testing, we develop the conclusion. And at the end of this example, again, I will talk about how does critical thinking help. Now, the internet's full of crazy ideas. How are we to sort the fact from the fiction? Is the world flat? Even what about ideas about hollow earths and whether or not that's feasible? Is the world really run by lizard aliens in disguise? Like, who thinks of this shit? Did dinosaurs live besides people, and is the fossil record faked? Possibly, unlikely. So looking at the observations of the Earth, well, the horizon certainly looks flat. However, I can only see limited distance and I can see further when I am up high. I can also see more of a distant object when I am elevated. Time zones and sunrise and sunset are different across the planet. We will discuss which situation, flat Earth or round Earth, that could feasibly occur in. A stick in Perth and a stick in Melbourne of the same height at the same angle have different shadow lengths at the same time. What situation might that be the result of? Objects on the horizon appear to rise as you get closer. They don't just appear out of nowhere. Star constellations are different depending on where I am located globally. So would flat Earth or round Earth be more likely to cause that sort of phenomena? And lastly, photos from space indicate the Earth is round and it appears to spin. For this example, I'm stating there are 2 hypotheses. The Earth is flat and the Earth is round, both of which we can test fairly simply. When investigating things like facts or fake news, whether or not it is actually fake, there's a few things you should really consider. How reliable the source is, does the claimant have an agenda, and also do they actually know what they're talking about. For example, with COVID-19 at the moment, you wouldn't go interviewing a chemist on what they think about the pandemic because a chemist isn't an expert in epidemiology. You'd be more inclined to seek the expert opinion of a immunologist or a microbiologist or even an epidemiologist. Is there independent confirmation of the facts? And also, has the hypothesis been disproved and has anyone tried to disprove it? For example, cold fusion was announced to have been discovered in the 80s and it was later unable to be reproduced. So someone's released a study, other people have tried to produce or reproduce the results and they couldn't. And this happened multiple times, so that means that even though someone released something which may have been a theory, while the theory was disproved, kicks it back down into the hypothesis stage, which means that either the original hypothesis was invalid or something in the experimentation was flawed. And in this case, well, it's 2020 now, so 20 to 30 years later, no one's reproduced it. So in this case, the original hypothesis must have been wrong because no one's ever reproduced the results. Currently, there is a reactionless drive that, if proven to function, could revolutionise space travel. Scientists seem to be having a hard time disproving the engine works, but they are also having a hard time reproducing the original results. New physics are apparently needed to explain things, which in turn complicates things. As discussed, Occam's razor states that the simplest solution is probably the right one. The simplest solution in this one would be that the apparent force the reactionless drive produces is an error. Because if you've got to create new physics to explain how something works, generally it doesn't. And also, does the idea account for unknowns in the current theory? Potentially with that last example. A better example there would be theory of the universe, as in quantum mechanics versus macro physics. Both explain things within their purviews, but you can't put them together. So ideally, someone somewhere would come up with a new hypothesis, which would then turn into a theory which explains everything. And it could be, hey, we're all in a simulation. Stuff at the micro level is not really shown to be too precise because that's the way that the system was programmed. However, that's not really provable, and you can argue how likely that it is. So, testing through experimentation. I will describe some experiments that you could conduct on your own. If everybody wanted to do the experiments and compare notes and develop a conclusion, that makes this whole thing peer-reviewed. So let's look at a hill as far away as I can with binoculars or a telescope while on the ground. Then I could climb a hill or a gantry or a scaffold or something and observe the differences. Experiment number 2 would be sticking nails in a melon or an apple or something 2 centimetres apart, and I could shine a torch on the melon from 2 metres away. Bang nails into a flat piece of wood. We could observe the shadow lengths under the sun. And using this setup from 4, I could bring the wood to eye level, observe the nails, raise my head, and observe the nails again. What would happen to the far nail if the wood could be bent so the nails fall below the horizon? Previous experiments show that the sun is rather large and over 8 minutes away by light speed. This essentially means that the sun's rays are parallel by the time they get to the planet. If the rays are not parallel, the results of this experiment are invalid. So we've got to make some assumptions on what's going on. We can see that in our diagram here. We've got a round Earth, we've got a sun, not the scale of course, and I've indicated sunbeams, which are parallel. I've also shown 2 sticks in the ground, so you can see that, say this one here, this is our stick. It's exactly the same length as this stick here, exactly the same angle in relative to this line, which is the ground. Because the beams are parallel, they come down here, and this is our shadow length. This stick, which is supposed to be pointing directly up, has no shadow because of the parallel sunbeams. So this would imply that the Earth is round. Whereas in flatland, we've got the sun, we've got our parallel light beams, we've got sticks all at the same height, and say 50,000 k's apart in this example versus 5 k's apart, not the scale of course. And you can see that because the lines are parallel, shadow lengths here, shadow lengths here, shadow lengths here, they're all exactly the same. So this would imply, based on the observations we make in the real world, that the Earth is round. Same thing if this was a stick or an apple or something and you had a torch 2 meters away, you get exactly the same result with the experiments, or similar. Next up, sightlines. Sightlines are based on the curvature of the Earth and also long distance visibility. So things far away might get hazy, but they're not going to, say, rise out of the ground or just appear out of nowhere. Assuming no atmospheric interference, visible objects would appear visible in their entirety. A receding object would get smaller and smaller. Far objects away on a round Earth, though, aren't visible after a certain point, as they would fall below the horizon, and a receding object would appear to sink. So what we have here is our flat world and our round worlds again. So here's me or you or an observer, flat world, sitting on our elephant, of course. 2,000 kilometres away, there's a big tree. So it's probably going to look pretty small, but because the world's flat, assuming there's nothing in the way, like a building or a house or an elephant or even a duck that would occlude this, then you'll be able to see that tree. It could be 20,000 million kilometres away. With a sufficiently powerful telescope, you'd be able to see the tree. On the round world, however, there's absolutely no way to see the tree because the tree is below the horizon. And what this means also is, with our example here with the boat, you can see a boat here when it's really, really far away. You get a bit closer, exactly the same image is there, but it's bigger. And you get even closer, same image, it's just enlarged in size. Whereas on a round world, what happens is objects further away appear to sink below the horizon or sink into the ground because of the curvature of the Earth. So if the tree was here, a little bit of the base of the trunk would be disappeared. If the tree was here, a little bit more has disappeared. If the tree, say, here, you might be able to see some trees at the top, some leaves at the top. But when the tree's here, like you can only see this direction, you can't see all the way over here because light doesn't bend around corners. So this also would indicate the Earth is round. So based on our observations, what do you think the answer is? Is the world flat or is it round? It's round. How does critical thinking help us in this? What we have done is develop our own experiments to determine the validity of others' ideas. I've tested two hypotheses, one the Earth is flat, one the Earth is round. I've made no assumptions about what could be correct at the start, and that's also important. The conclusions are based on evidence that can be scaled up. So here, if you did want to test it on a watermelon, you can then scale it up to the globe if you had the sufficient equipment, or if you rang somebody up and say, hey, so-and-so in Perth, it's midday here in Melbourne, what's that stick we planted in the ground pointing directly up that's only 2 metres in height in your backyard versus a stick in my backyard that's exactly 2 metres in height sticking up directly from the ground? I've got no shadow at midday, or what have you got? And they say, our shadow is about 32 metres long or 2 metres long or whatever it is. But it would show you that the shadow lengths are different, which would indicate that there's curvature. In this case, it doesn't make sense at all that the Earth is flat. There's no evidence of people sailing off the edge of the Earth. Satellites orbit the Earth. The Moon and other planets and the Sun all appear to be round, so it stands to reason that the Earth is too. Photos from high altitude in space show curvature. Gravity pulls down to the centre of mass. Easy experiments all indicate a curved surface to the Earth. So you could build your own rocket and try to launch it and see what happens, but I wouldn't advise on doing that. Okay, regarding flat Earth facts in quotation marks. How reliable is the source? Does the claimant have an agenda? Well, in this case, generally you don't know. Is there independent confirmation of the facts? Not when it's flat Earth. Has the hypothesis been disproved or falsified? Yes, multiple times, and we just did it here. Has anyone tried to disprove it? Yes, I am just one example. Can it be tested? Again, yes, we just did it. Does the idea account for any unknowns in the current theory? Well, no, because there are no unknowns. The round Earth hypothesis came along after the flat Earth and matches the observable data. So, back in the old days, flat Earth was a perfectly reasonable theory. It's since been disproven. Therefore, the old theory gets booted out, and you get a new hypothesis comes in, which gets shown to be true, and then that's a new theory. Next up, I am bad at climbing hills. So, what's our quality assurance with regards to determining or addressing why I am bad at climbing hills. I need to observe the phenomena, I need to develop a hypothesis, I need to test through experimentation, and in the end develop a conclusion. And again, I will sum up why critical thinking helps, or how it helps. So what are the observations in this case? When cycling up hills, I tend to be slower than others. When I weigh more, I climb slower. I climb faster when I am light on a bike. When I am racing well, I seem to climb better. Sometimes observations don't contain hard data, and sometimes the problem needs to be rephrased. So here I've said that I'm bad at climbing hills. I'm going to rephrase that to be I am slow when climbing hills and I want to be faster, because that pretty much states the issue and what we want the outcome to be. And for this discussion, racing well cannot be measured or defined. When the light globe example was used, we clearly knew what on and off is. We don't know what racing well means. It could be winning, it could be producing decent power for a decent amount of time, it could be something else. So if you're going to observe something, you should really also try to measure it, which is why I've rephrased the statement to I'm slow when climbing hills and I want to be faster. In this example, gathering data is definitely king. So what are our observations of the phenomenon? When I cycle up Mount Payne, I'm often a minute slower than other cyclists of presumably the same height and weight or similar abilities. When I weigh 90 kilograms, I climb slower than when I weigh 80 kilograms. I climb faster when I am on a light bike for the same measured effort. I cycle up Mount Payne 45 seconds faster at 300 watts than at 200 watts. So these are all the observations. From this, we need to develop a hypothesis. So based on the observations, my weight affects my climbing speed, and power output determines climbing speed. Here, a little research shows that a cyclist's power to weight ratio, or watts per kilogram, affects climbing speed. Here, the initial work has already been done, and we can therefore determine ways to improve on the watts per kilogram figure. So what I really have here are two proven hypotheses already, and because they're proven hypotheses, they're actually theories. What do I want to do to improve my climbing speed? Do I want to increase my power output? Do I want to decrease weight? Or do I want to do both? Presumably increasing my power output and decreasing my weight makes me extra fast. The flip side of this is less weight could mean less muscle mass, which could equal less power. More or the same power at less weight equals faster climbing speed. And that's why skinny cyclists tend to ride up mountains faster than larger cyclists. Theories are great. Theories mean other people, normally lots of other people, have shown ideas or concepts to be reproducible. This means you do not need to conduct such testing yourself and can use the theories to help you create more data or solve an existing problem. If my power stayed the same or went up, I'd find it easier to climb a hill and be fresher at the top. If I wanted to ride the hill hard, I could knock even more time off my climb. And a race can be won on a long enough hill. I found I can maintain my power output when I get lighter, and I'm on an internal quest to get 5 kilograms lighter. I like my food and my chockies a bit too much for that though, so ideally I would improve my power. As we now have a theory, here we are implementing corrective action. The weight now is 80 kilograms, my power output's 250 watts. So what is the time to climb Mount Payne? Well, it's 5 minutes on a calm sunny day. What's easier to do, get stronger or get lighter? So I'm only testing one variable here, I will eat less. Through training I might get stronger, but for the testing I want to keep that consistent. So months have now passed, I'm weighing 75 kilograms, so yay me. I'm climbing the hill again at 250 watts, and it gets me up the hill in 4 minutes 30 seconds. The weather conditions were the same as the initial testing, so that shows you that less weight equals faster climbing for the same power. And we can also assume that as I've concentrated on my hill climbing, my power output has increased, so I could actually go up a hill harder than I could back when I was 80 kilograms. Now to develop the conclusion. Here I want to see if the corrective action attained the desired goals. Did I lose weight? I most certainly did. Did I get stronger? I didn't test that, so I can't make any conclusions. How long did it take me to climb up the hill now that I am 5 kilograms lighter and producing the same power? Well, it took 30 seconds less. So the conclusion here is, at 250 watts, Mount Payne can be climbed at 75 kilograms, 30 seconds faster than when I weighed 80 kilograms for the same environmental conditions. Was the corrective action successful then? Yes, it was, because I'm climbing hills faster. Which is all great, because as an athlete, the goal was to reduce my weight and climb hills, in this case Mount Payne, faster. The goal was based on existing knowledge regarding power to weight ratios and climbing speed. And our conclusion demonstrates that the goal was met. Demonstrating that you can meet your goals is important when running projects or setting out to achieve something, so it can help you both personally and professionally. How did critical helping benefit us during this example? It enabled us to rephrase or redefine the problem. By developing measurable actions with measurable outcomes, I could show whether the actions taken were successful. And showing positive outcomes is important when it comes to things such as website click-through rates, return on investments, determining the success of training, things like that. A negative outcome can help refine and improve future plans to improve the likelihood of a successful outcome. So if you found that I got slower climbing hills at the same wattage for less weight, you'd be going, our hypothesis was probably iffy. If I was a coach, say, I could show how my training plans work. I could also improve upon them over time, therefore improving my services and improving my athletes. The final example here will be a computer software installation fails. Again, because we are consistent with our approach to troubleshooting, on observing the phenomena, developing a hypothesis, testing the hypothesis for experimentation, and based on the results of the experimentation, I am developing a conclusion. So what do I have here with regards to observations? Normally when a program fails to install, there is an error message. So what exactly is the error or problem? You would need to gather information to eliminate the variables, e.g. is the software supported on the operating system? Have prerequisites been met? Is something else there that we need to consider? Can the issue be reproduced? Can a hypothesis of the root cause be formulated? And does the fix based on observations and a hypothesis actually fix the problem? With software, if it's well written and is fully debugged, all prerequisites met and the correct installation procedure followed, then the software should install. Pretty much failure to install boils down to 1. A known issue with a known solution, or 2. Something was not followed and thus we have a prepackaged solution, or 3. Something totally new, which I will expand on right now. So with developing the hypothesis, based on observations, we've got our 3 possible causes. Something that's known, something that hasn't been done correctly, and something new. Ideally, if you were troubleshooting this sort of situation, you would test the most likely hypothesis first before trying another solution, which should lead to a faster solution for the customer. So you wouldn't say, hey, here, try this most complex solution to the problem, which is probably really easy, and if you had to follow this really easy solution first, the problem would not exist. You want to give this easiest solution and most likely solution first. Existing work and knowledge, again, is useful. From experience or from existing data and test results, we know that a failed installation comes down to these 3 points, which speeds up the current process. Also, are there any bugs, incompatibility, incompletely downloaded and install the file would be, say, a known issue. Number 2 would come down to a lackadaisical following of procedure or prerequisite checks. And number 3 could be something new that makes things interesting, such as, who knows, that's why it's new. So we need to figure out what it is so we can solve it. And once 3 is solved, then it becomes something in the category of number 1, something we know. So solve the problem for this new thing, then we know a solution in the future, which means troubleshooting in the future is fast. If it is a known issue, chuck out the standard fix. Did it work? Okay, we'll go on to number 2. Something not being done correctly. So you're installing software onto Windows XP, which is meant only for Windows 10. Well, that's the solution right there. Don't use an unsupported situation. And for something new, we need to determine what was the cause of the issue by gathering data. If we can reproduce the issue using the same setup, brilliant. We could also offer workarounds if there is one, while we actually nut out the root cause and then provide the problem solution. And here we have a nice little slide. So the problem is, it's a known issue. Okay, yes it is. Provide standard fix. Did it work? Yes. Hey, we're done. Problem, known issue. Yes. Okay. Provide the standard fix. Did it work? No. Okay. Have prerequisites been met? Yes. Okay. Test for other causes of the case. Other causes of the issue, because now it's a situation 3, as in we don't know what's going on. Problem, is it a known issue? No. Have prerequisites been met? Yeah. No, they haven't. Follow the installation documentation. Okay, we're doing that. Did the problem go away? Oh, surprisingly it did. We're done. On to the final situation. Is it a known issue? No, it's not. Have prerequisites been met? No. Okay. Did we follow the installation documentation? No. Okay. So the problem go away? No. Test for other causes of the issue. So it's probably the shakest example, because what we should really be showing is if it's not a known problem and we didn't meet the prerequisites and we didn't follow the correct procedure, well, of course it's not going to work. So you want to go down this path ideally, maybe down this path. If you go through this path all the time, you're not going to get anywhere. So it's going to be a waste of your time and everybody's time. So with developing the conclusion, we could then update the troubleshooting guide. I like my troubleshooting guide or guides to be an indexed database, not unlike something you'd see in Evernote or OneDrive. That way I can reference solutions to known issues and update the databases with improved situations or solutions and add entries for new issues. I also supplement that with various resources such as this example, say a Kaspersky online help page, admin guides and internal help systems. Keeping troubleshooting guides up to date ensures a consistent approach when determining the problem and allows for consistent troubleshooting steps or solutions to be given to the customer. Indexing the known solutions speeds up troubleshooting for known issues and ensures consistent data gathering for unknown issues. So less time trying to figure out where you recorded the solution. This information can be easily shared with and used by others in my team or sold to other organisations that do troubleshooting. Okay, how does critical thinking help when we're investigating a computer software installation failure? It speeds up providing a solution to known issues and allows new issues to be problem solved in a consistent manner, which enables efficiency, which means you save time and money. If the same issue is unknown today and a solution can be developed, then next time it's a known problem, so a solution can be provided right away. There's no need to troubleshoot because you know what the answer is, or what the most likely answer is going to be. In conclusion, quality assurance allows for a consistent methodology for problem solving. Scientific principles help troubleshooting by breaking down the analysis process. Combine both of these and you get efficient and consistent troubleshooting. Critical thinking allows you to make the best decisions while problem solving. Critical thinking examines facts as well as the data you produce. And scientific thinking can benefit everyone. Thus ends my presentation on using quality assurance principles in troubleshooting. I hope you've enjoyed, and we'll catch you next time. If you have found this presentation useful or interesting, hit that subscribe or like button, share the video, or provide some comments. I consider all feedback as positive, as without a feedback loop, improvement is difficult. Until next time, this has been Paul Yeatman, Bachelor of Science, scientist, seeking a return to the lab. Kapla!